Hello, welcome to this brand new episode of Corecast. I'm your host, Tim.
Mikey.
This is Sahil. Welcome everybody to a brand new exciting episode of Queercast. If you haven't and a few bit of logistics before we get started, if you haven't already, do join our Discord channel so you can ask us questions there. And if you're watching on YouTube, where we do this at 5 p.m. Pacific, 8 p.m. Eastern every Tuesday, then ask us questions during the episode when we get to that as well. So without further ado, I guess Tim, we were talking along with Mikey about this notion of like a God's particle, how like the Higgs is called the God's particle, like at least by popular nomenclature. So I want to kind of like start with the question like what would we consider actually kind of going to the end of this episode, like what we would consider as like the true God's particle. Before that, can we start with the history of like what is the notion of a God particle to begin with? Like why would anyone call a particle a God particle? Either Mikey or Tim.
Okay, so there is no notion of a God particle. There is no such thing. Like no one in physics,
Not from
no one in
physicists.
physics called
Not
any
from
particle the
physicists.
God particle. Um, what happened was sometime in the late 70s or the late 80s, I forget which one. One of the most prestigious experimental physicists wrote a book about the quest to discover the Higgs boson, and he happened to name his book "The God Particle." So his name was Leon Lederman. Very well respected experimentalist. Um, but it was essentially a, I don't want to say gimmick, but yeah, let's be honest. It was a gimmick to sell books, right? It was the idea that this particle is so important. It's so important to the existence of humans um, that, I don't know, I guess according to him, you could refer to it as the God particle.
Yeah, but I think there's a little bit of just kind of the human context, right? Like, because during our stage of experimental particle physics discovery, it turned out that the Higgs boson was kind of the last missing piece. So I would say that nomenclature, the God's particle, kind of embodies some of that excitement going in. Like people were like, "Oh man, like that's the one we have to find." So I feel like, it's not literally the God's particle, but the name has stuck, really, isn't it?
I think
So
there's more to it than that, though, right? Like the fact is, like, the Higgs boson is what stabilizes the scale of all nuclear interactions, and that is what is most crucial. Like the fact that nuclear forces exist is the thing that is most crucial for the development of complex chemistry in life, and the Higgs is kind of like the linchpin of what keeps nuclear interactions at the scale that it does. So it's not a bad candidate for the God particle. It's just that there are better ones.
I guess like so I want to just clear up a few things. Like, is it true that when you say because they say the Higgs particle is what gives mass to things? Is that true? Like, is that like what was the deal with that?
Yes, so it's not like there's other ways that things can have mass,
Mhm.
but what the Higgs does is okay, so if we think about scales, right? Like, we live on the scales of like, meters, and we're made up of atoms that are on the scale of like, angstroms, and there's lots of different scales in nature. But the Higgs is responsible for making sure that it's responsible for making sure that the atom's mass is at the right place to be able to do chemistry and to be
Hmm.
able to give rise to complex life.
Gotcha. So Higgs set sort of the scale of different masses such that you can get complex chemical interactions and can give rise to.
Exactly. It sets the hierarchy of scales that is necessary for complex interactions to occur.
I see. So then like that seems pretty godlike, at least from
It
like
is, yeah. I don't have too much of a problem with it.
I
yeah,
don't know. It's a little human centric for me, right? Like God didn't have to create
It
humans,
is,
but
yeah.
but 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 this Higgs God particle, what kind of yeah, to some extent is responsible to kind of like a human compatible world to exist. So it's responsible for that. So I guess it's fair to some extent if there is a deity particle we worship, we'll certainly pay some respect to the Higgs, but it's not the crucial it's not even the most important ingredient for a universe to exist, which I think is a little
Absolutely
bit
not, yeah.
grander.
But to be fair, like most people believe that God is human-centric, right? And that God has this special attention being paid and care being put towards like, humans. Like in the Christian Bible, right? Humans have kind of an elevated status amongst the animals. Which, that doesn't really make sense because animals owe their existence to the Higgs as much as we do. But
Yeah. Okay. So I guess so Higgs could be considered a candidate as a God particle. Like we can jump into the whole human-centric notion. So let's put that aside for now. What would be other candidates that you would consider or candidate?
I would say we want to look at something that actually shape the structure of the universe, like, or the fact that things exist at all. And there are certainly other particles that could do that in particle physics. So those would be much better candidate.
what are some of those? We talked about one of them, which is, inevitably going to be the topic of this. But aside from that one, I don't know. Should we go through some other possibilities?
Yeah. So I guess the topic of today's discussion is the inflaton, which is a hypothetical particle. And it's probably one of the most leading candidate on how the universe came to be. But I think there are other potential candidates. Like, is the axion like a reasonable one?
If it's responsible for dark matter?
Well, beyond that, I think there are models where axions could also create other matter, but not necessarily.
Yeah, that's a tough sell.
Yeah, so that's a little bit of a tougher sell. But beyond that, like maybe the graviton, because it embodies.
Oh, the graviton's a great candidate for the God's particle.
Yeah, it embodies kind of gravity, but it doesn't have that oomph, right? But like, because any universe is gonna have a graviton, like any gravitational universe will have graviton. So it's kind of, I don't know how you want to put it. Graviton is kind of just the universe itself.
Yeah, the graviton doesn't really give rise to things, though, right? It's I mean, that's not true. It does, but
so it's not special enough. It just So I wouldn't say that's a good name for the gods.
Graviton is more like the universal communicator, like the universal messenger.
Yeah. Like the angel's particle, maybe. If we want
if
we want to go down that route.
Yeah.
So God, I think the God's particle.
Are we really getting into a trinity here, where it's like the Father, the Son, and the Holy Spirit? Where
let's not go into the analogy.
The Holy Spirit.
Stick to the physics, right?
No, but I mean, if we can draw analogies to things that people are familiar with, that's valuable, right? I think there might be a story here.
Yeah. So I guess coming back to this inflaton, what is that? Like, why is it so special?
The inflaton is the particle that gave birth to everything we know now.
How can that be? That seems too great to be like a
So I would say the inflaton is kind of like it's a theoretical proposal that somehow we're able to like kill two birds with one stone. Although we're not advocating for violence to creatures, obviously. Just a phrase.
Certainly not to birds.
But yeah, certainly not to birds. Birds are lovely creatures. But the inflaton are able to kind of solve two puzzles. I think one of the puzzle was, why is the universe so large? I mean, it might seem like a super obvious question, but it's not. When you look at quantum physics, universe could certainly be very tiny. So the fact that our universe is very large is kind of crucial for our existence. And the second puzzle is, why are there things in the universe? That might seem obvious to you that, why not have things in the universe? But like we mentioned before, you could literally just have gravity in the universe. There's no real reason why there needs to be things. So it turns out that by introducing this one concept, you can reason these two things out as consequences. Right.
Wait, no, it's killing three birds. You're missing one. It's also it's exactly the reason why the universe looks the same everywhere.
Yeah, that's a little more technical one. That's true. It actually is.
That's really the biggest experimental evidence. Like, there's no way to get that to happen without the inflaton.
Wait, quick question about this before we jump forward. For the second question, like why is there stuff? Wouldn't like gravity imply that there is stuff in the universe?
No, there can be empty universes with
Yeah.
gravitons for sure.
Just gravity, yeah. So it'll be a kind of boring universe, but you know.
Yeah.
I see. I see. So like I guess what is it like? Is it a particle? Like what are we talking about here when you say
With the
inflaton?
inflaton,
Yeah. Like
the inflaton is basically, I mean, it's basically vacuum energy, right? It's just this constant. You just assume that there was this constant, steady amount of energy that you ascribe to space and time in the early universe. And that's the other thing about the inflaton. It's such a simple hypothesis. You just assume that in the very early universe, the energy density was high. You know, whether it's because of quantum fluctuations or whatever, but there's so many natural ways to make it so that the energy density of the universe was high in the beginning.
Mhm.
And what that does is it creates this very exponentially fast explosion. It makes the Big Bang like way faster and way more intense than you would have thought. Stretches
Mhm.
everything out to like a very, very massive scale, stretches the universe out to a very massive scale in a very short amount of time. And it ensures that every single part of the universe looks exactly the same because it stretches it out so fast that variations don't even have time to form yet. And then after it's done expanding, it basically decays into all of the particles that we know and love today.
I see. I see. So I want to actually ask you a question for our audience in case it's not familiar. Like when I look out at I think a sense of scale would be helpful because when I look out at like different parts of the sky, they look all different. But like, what scale are we talking about here when you say everything looks the same?
Yeah, I would say this is the scale of the observable universe. It's when you look out to the telescope to the farthest galaxy that you can see, or you look at Hubble, in every single direction, all the different
Mhm.
types of galaxies, how bright these galaxies are, the interactions between these galaxies, it all looks similar. The physics behind them, basically, and this is not a given, right? Like we could imagine that the stuff in one direction of the sky versus the other direction of the sky could look a little bit different, and that wouldn't be crazy because the universe is so large, and it doesn't cause humans any type of predicament one way or another if the stuff one direction of the sky is different from the other direction of the sky, right?
Mhm.
But indeed, we see from observational evidence that the universe looks kind of darn similar in every single direction. Like, of course, you have planets, you have solar system, you have galaxies, right?
Large
These are
scale structure.
yeah, but when you zoom out, and kind of squint your eyes a little bit and kind of look at the average properties of the universe, it's pretty darn consistent, right? So
Mhm.
that's one of the marvelous fact about the universe, like that it's large, it's got stuff in it, and also it looks pretty similar almost everywhere. And and from that we can kind of guarantee that if aliens were to exist, they'll see a very
Mhm.
similar universe than we do.
Hmm. I
Even
guess
more than a distribution of matter, though, like, what's the temperature of empty space? It's like 2.75 Kelvin or something.
yeah.
It is 2.75 Kelvin everywhere, like plus or minus 0.00000. Like, it's almost completely uniformly the same temperature.
Hmm.
How can that happen? Uh,
Yeah, that's actually really hard, really not easy, right? Like imagine you're heating up like a pot of water. Chances are like the bottom of it will be a little hotter than the top.
exactly.
And imagine if the Big Bang were to happen one way or another, you can imagine some energies in certain pockets of the Big Bang might be a little more energetic than the other. And these differences could easily get amplified, more and more amplified into like super hot spot and super cold spot. And if that were true, you're gonna see a pretty wacky universes with like artifacts in the sky, like this, I don't know, holes or like defects that here and there. I don't know, like some kind of portals or something. Like that's
Yeah, it might be like 5 Kelvin here, 2.5 Kelvin here, maybe 10 Kelvin there, like things like that. If you give it enough time, these kinds of like variations will form. But if you blow up the universe so fast before those variations even have time to form, that's one of the most compelling ways to explain why like this temperature is so goddamn uniform, like across such large scales.
So I want to ask a question just to get a sense of like of scale again. Like, how fast of a blow up are we talking? Like what's like?
Faster than you can imagine.
Oh
It's like,
yeah, it's
we were kind of describing it this yesterday, right? Like, so you imagine you're like chewing a piece of gum, right? And you're chewing it, and then if you just take out a lump of gum, there's going to be like parts that are really dense and parts that are not that dense, and there's going to be like a lot of, you know, different features to this gum. But if you blow the gum into a bubble, right, all of a sudden everything is like, at least on the surface of the bubble, suddenly becomes like super uniform. And I think that's like a fair analogy for how to describe the way inflation solves this problem. If you just like blow things up super fast, like everything becomes very uniform because it all comes from just one central location.
and I think it's important that the universe kind of get blown up and diluted a little bit, because with all that energy, chances of the universe would not be very kind to complex existence. There could be there could be too much matter, causes the universe to crumble, or there could be so much vacuum energy it would just explode into nothing. So kind of this exponential blowing up it allows space to grow basically, so that things could actually take time to form. Interesting things anyway. So that's important.
So I guess like so we've explored the question of like, why does the universe look pretty much the same in all directions? But I want to explore the other two questions as well to see how this answers. So the question is like, why is there stuff? Like, even if you didn't expand and there was like one central clump, that would be stuff. Like, so how does this inflation or inflaton explain that, or like explain the notion of stuff to begin with?
Yeah, and I think physicists are concerned with this ultimate philosophical question, like how can there be something out of nothing? And if
Oh, he's talking about reheating. There's a very straightforward story to that.
yeah, I
Might be a
mean,
little technical, but
yeah, I mean, stuff carries energy, and that energy's got to come from somewhere. And I think it's commonly agreed upon that this paradigm of inflation, this hypothetical idea, I think generally is viewed as the era before Big Bang, basically. I think that's fair, right? So this is what happens before the Big Bang. When you have the Big Bang, you already have the energy in stuff, and all that's left is to expand it. So the question is like, well, then where does all these energy come from, right? And in physics, some people have the misconception that the Big Bang postulates that something comes from nothing. That's not true, right? The thing that comes before something, the candidate is the inflaton, right? The inflaton is a very simple proposal. If you just have this vacuum energy that somehow interacts with some other stuff, it could be the Higgs, it could be the Higgs field, the Higgs boson, or some other particles, but it doesn't matter. It doesn't really matter much what it interacts with. Then slowly, the energy that were stored in the inflaton field could kind of get transferred into the energy stored in other particles, and slowly stuff can get created, like all kinds of particles, like electrons, quarks, and gluons, and all that, different force carriers, photons, and whatnot. And slowly, the universe heats up. And keep in mind that the universe doesn't just heat up like here or there, right? It kind of heats up everywhere, like because we see galaxies here, like, in all kinds of directions. So this heat up, it's gotta be pretty damn dramatic, right? It's not just like one tiny little spot heating up. It's gotta be heating up everywhere. So the inflaton kind of provides this, how do I put this? This omnipresent energy content that slowly just transfers into the stuff that we're familiar with, and also dark matter to allow structure to form. And this is where the real creation story happens in fundamental physics.
So I want to ask a quick question about that, like as from a skeptical point of view. So from quantum mechanics, I remember that like particles can pop in and out of existence. Why can't you make the same argument with like the creation of the universe, that there was nothing, and then boom, like particles appeared out of existence, and then like that formed our like universe?
because the conservation of energy, right? Like particles can pop out of existence, but because of conservation of energy, that can only happen if they annihilate and hide any, quickly hide any evidence of the fact that they existed. But if you actually want to create, particles that have longevity, then you need some initial energy density to seed those.
I see. But hold on. I thought we had discussed on previous episodes, like because we see the universe expanding, that energy is not conserved. So what gives with this argument?
Yes, that's a very good point.
Yeah,
But
yeah,
um it doesn't relate to, but from what you were saying is that particles could pop in and out of existence. You're talking about if there's like, let's say, an energy density of like 10 joules in
Mhm.
this box, right?
Yeah.
Uh, Conservation of energy says that if I can create more energy for a split second, but it has to even out to like 10 joules per square centimeter or whatever in the end,
Mm.
right?
yeah. I mean,
It's true.
this non-conservation of energy doesn't help you, right? It dilutes energy more, even more. So you still can't. At the end of the day, you still can't just create stuff out of nothing.
No, I mean, well, in a sense, that's what the inflaton does do, right? Because the inflaton is the energy of space itself.
Right.
So when you create more space, you're creating more inflaton energy. And I think that's what Sahil's referring to as the non-conservation of energy. Is the stretching of space literally generates more energy.
I guess that's a fair interpretation. Yeah. So the theory
It's
of
vacuum energy.
the theory of the inflaton takes into account gravity and this
Mhm.
new hypothetical inflaton, and also the matter content that we see. And indeed, through quantum mechanical processes, all these combined will create you like something, will create you stuff that we know and love. And in a way, you can think of it as energy non-conservation, right? I think to some extent that's fair, because in gravitational physics, energy is not necessarily totally conserved, right? But on another viewpoint, you can kind of think of it as the energy from gravity kind of transitioning, and the inflaton transitioning into matter and existence.
Huh.
Here's a
So
way to think about it, right? So like, um, the inflaton is very similar to like what we call the vacuum energy, just the intrinsic energy of empty space, meaning that if you stretch the space, the energy increases.
mhm.
That's different from like ordinary matter. Ordinary matter, you have like three particles in a box, right? You make the box bigger and
Mhm.
that energy dilutes. Now it's a less amount of energy per unit volume.
Mhm.
The inflaton and things like the vacuum energy are different. They're the intrinsic energy of empty space. So if you create more empty space, then you're creating more energy. If this happens too slowly,
Mhm.
then all that energy you're creating basically starts evolving under like its own, it can grow to be very different in different regions. The reason why the inflaton is so beautiful is because it predicts that there is this intrinsic energy density of empty space. That intrinsic energy density makes the universe blow up so fast that
Mhm.
within less than like a billionth of a second, now everything is uniform everywhere. And now everything can start to decay at roughly the same time and kind of create this uniform universe that we see.
When you say everything decaying, like what does that mean? Actually, like maybe it's helpful to the audience, like kind of explain the picture of like what happens, like at least chronologically. Like you have inflation, then the Big Bang, and then this decaying, or like how do events proceed?
Yeah. Yeah. So I mean, it's a little technical when we say
Well, no,
inflaton.
generally anytime the temperature drops, right, you have you have certain high levels of energy decaying into like low levels of energy, right? Like if I turn up the temperature right now, I'm
Mhm.
going to create like a bunch of top quarks,
Yeah.
right? But then if I lower the temperature, those top quarks will decay into lower energy states just because of the energy that's in the environment. I think that's very much what happened with the inflaton. It's like the inflaton creates this massive expansion, and
Mhm.
then eventually that massive expansion, I mean, the energy density starts to drop and then things cool down and the inflaton starts to decay to everything it can decay into, which happen to be the particles that were necessary for the creation of life and complex structure.
Oh, so you're saying at like higher energies, there would just be the inflaton, and then because it expanded the universe to such a large scale, uniform everywhere, universe started to cool down, and then the inflaton itself decayed into the particles that we know. Is
Yeah.
that?
Yeah, I mean, okay, that's a little misleading. It doesn't cool down just because of the expansion. You do have to hypothesize that there is some like potential, right? You know,
Yeah.
Tim, that yeah.
Yeah, probably temperature isn't the best word because temperature is not really well defined at that point because there's no stuff yet, so you can't define the
Yeah.
temperature. It's more like there's a dial on the inflaton, right? The inflaton has kind of a bit of an instability, and at some in the beginning it's high, it's hot kind of, but it's not temperature hot. There's this dial inflaton that's hot because it's unstable. It slowly kind of goes down, so it's kind of like cooling down, but not like temperature cooling down. There's this inflaton dial that's cooling down. And at some point, after it dials down enough, and as this dial goes down, because of the instability, it wants to go down, the universe expands. And at some point, this expansion kind of is coming to a halt now, finally. So it stops expanding. It's good. It says it's good enough now. And then when that cooling down happened now, things start to like pop out now. Things start to form because that's the next stage of evolution for this instability. This energy gets converted into ordinary matter, like quarks and gluons and light and all that, and this is kind of the creation story.
I see.
So the theory of the inflaton is exactly like the theory of a ball rolling down a hill. Okay, so the ball starts at the top of the hill. That represents a high energy density, right? That high energy density causes the universe to expand at an exponential rate, stretches any kind of like small variations there are, got stretched out like bubblegum blowing into a bubble, makes everything uniform. And it does that until the ball rolls down to the bottom of the hill. And once the ball rolls down to the bottom of the hill, now the energy density is lower everywhere, which we can interpret as a lower temperature. And you know what happens to a ball when it rolls down to the bottom of a hill? It kind of like goes back and forth, creates friction, right? And that friction basically blasts out, lower energy particles, more stable particles, like the ones that we're familiar with.
I see. So if I take this in the context of the Big Bang, before the Big Bang, it's hypothesized there was this massive inflation. And then when you get to the point at the time of the Big Bang, is that when things like decay, or is that further expansion, or like what are we talking about here?
That's the question. What's the end of inflation? And we would call the Big Bang actually the reheating phase, right?
Yeah, I think it's a little murky. Like at the end of inflation, the ball bounces back and forth, creates friction. This friction just creates a lot of random stuff, particles, and I think this is the period we call reheating. And there are multiple stages. I think when that's done, kind of the universe heats up at a maximum temperature now because all that friction, all the energy. And this is the beginning of the Big Bang, I think, most commonly. And then the universe starts to expand even more and start to cool down. But this expansion phase is way less dramatic than compared to inflation. It's not exponential anymore. Right? It's just like maybe a little teensy bit, expanding. It's still fast compared to, human scale, but it's like way slower now. It's like controlled expansion, I guess. More like, as opposed to like runaway inflation, just like everything's blowing up.
Okay. So I guess like, what do you mean by reheating? Like, it sounds like the universe is like an oven, and like, quote unquote, like God came and said, "Oh, it's not hot enough. Let me reheat this." Like,
I mean,
it's not the best language.
Yeah, it's not. The thing is because like I said before, you cannot define a temperature when there's no stuff in it, right? When there's just the inflaton field and gravity. There's not enough stuff to really define the concept of thermalization.
You can define the temperature, which is the energy density. I mean, it's not what we understand as temperature, but
yeah, but it's not that great. So really, reheating just means like the first time the universe is hot. Like, yeah, like even as the ball is rolling down, pretty much there's no such like. I think you can is temperature basically zero or something. Like, it's not in equilibrium, so you can't really define it very much. There's no stuff in it.
I mean, if you just use the Boltzmann constant to transfer energy density into temperature, you can say that it is hot there.
Yeah, but I don't know. Yeah, but it's quantum mechanic. Yeah, I don't know how I would feel about it. I think
I don't know if reheating is a great word for it.
it's not a great word. It's almost like the initial heating, or maybe even heating is not a good word. It's just the creation. Creation is happening. I think that's the closest thing. Things are getting created.
Oh, so at the time of Big Bang, things are getting created in this concept. You have inflatons that expanded the universe uniformly, and then at the time Big Bang, things are getting created. Is
Yeah,
that
yeah.
fair?
Yeah.
Yeah, and I think literally this is really the closest thing of like I hate to use this word, kind of like a deity, this magical thing just creating stuff, right? This is like the invisible hand. It's not
It's
a
this
hand.
one substance that
Yep.
gave rise to all of the variation that you see.
Yeah, like if I were to make a video game with like the the biggest godlike power would just be this inflaton field, just be like decay and let there be stuff basically.
Yeah.
Ah, so I guess like then okay, so there was this massive inflation that happened early on, Big Bang. Then inflation would it say it slowed down relative to the pace it was at before? Is that
Oh
fair to say?
yeah.
Yeah, yeah.
Yeah. When the ball rolled to the bottom of the hill, inflation basically stopped.
Yep.
Ah, okay. Then what is this talk about the universe having accelerated expansion today, like as we have today?
So that's actually very much related to the inflaton, right? So
Oh,
right now, the universe has this what we call dark energy, right?
mhm,
And that dark energy is very, very similar to the inflaton in the sense that like it's the energy density of empty space, meaning you make more space, you make more energy.
mhm,
And that's what's making the universe expand at an accelerating rate.
mhm,
But it only started doing that recently, because up until recently, there was so much like matter and radiation in the universe that the energy density of dark energy was not large enough relatively to the other kinds of energy in order to make um, the universe accelerate in its expansion. So inflation is like the idea that in the very early universe, there was a much stronger form of dark energy.
mhm.
I think we can literally think of the inflaton as like dark energy on crack that existed in the very early universe.
Maybe
Oh
dark
my
energy
God.
is not the best word, right? Like this is positive energy, like it's benevolent energy. Dark, I mean, dark energy has a similar godlike power, right? It can mold the universe, but it's not really working in our favor, right? Like if we wait, let's say, many more billion years, the actual dark energy will cause accelerated expansion and will dilute the stuff in the universe, and ultimately that will lead to the doom, I guess, the inevitable heat death of the universe. So dark energy is kind of like, shall I say, like the kind of the anti-god, the Lord of Destruction.
But they're two sides of the same coin, right? Like
It
you could
is.
literally
It's
imagine
true.
that
Yeah.
that the dark energy, you can think about it as like the remnants of inflation. Like
Hmm.
inflation was a period when the dark energy was so high that the universe's acceleration was expansion was accelerating so great, and then the ball rolled down to the bottom of the hill, and that gave us kind of the value of the dark energy that we have now, which doesn't really have that much of influence on the accelerated expansion of the universe because there's so much other stuff in the universe now that can influence it. But as the universe gets bigger, that other stuff dilutes, and then the dark energy wins in the end. And so now we're starting to get into this accelerated expansion phase, which will ultimately lead to the doom. But it's like almost like this, it's poetic. It's like the same thing that gave us, same mechanism that gave us all this stuff will eventually dilute it out of existence.
Oh wow. So like we can't say that the dark energy today will like decay and create stuff like it did or like inflatons did in the past because it's not at a higher energy. It's at a lower energy now, right? Energy density.
Yeah, I mean, I
I
don't
mean,
know. There's
there is plausible, like not maybe not literally the dark energy, but there are plausible theories that this period of, I guess, creation could happen again in the
Hmm.
future that we don't know. But without those extra stuff, extra hypothetical scenarios, yeah, the dark energy is not going to do anything. We'll just see things getting more and more dilute. I think that's true.
Yeah, if you think about the current dark energy as kind of like the remnant of the inflaton rolling down the hill, like it was huge in the beginning, universe was blowing up, rolled down to the bottom of the hill. Now dark energy is like this weak, very, very weak energy density in the universe. So it's hard to imagine how it could suddenly get high again to create the kinds of conditions that inflation gave us. It's likely that it's just going to stay at its kind of pathetic value right now. And it's just going to win out of sheer patience.
Yeah. I guess the God particle only gives once. It gives and it can take. But
what Inflatons give it, Inflatons take it. So I guess one question that I have is like inflatons and gravitons, like would they be hypothesized to be the same particle, or did inflatons give rise to gravitons, or are they separate particles? What's the deal with that?
Question, what's the answer to that?
Wait, they're definitely different, right? Graviton is...
Yeah, but did inflatons give rise to most of the gravitons? Gravitons existed at the same time as inflatons?
No, I mean, graviton is always there, I think.
Right.
I mean, look, ultimately, we don't care so much about the particles. We care about the field that is related to the particle. So I would say the gravitational field will always exist. I think that's probably absolutely given, right? I mean, the inflaton field is hypothetical. We have not seen, we have not seen experimental hint of its existence, but we strongly believe that there probably is one out there.
Wait, so are you saying that inflatons did not decay into gravitons? I actually don't know the answer.
It probably did. I mean, it definitely create perturbations in the gravitational field.
Which existed first, the inflaton or the graviton? I don't know the answer to that.
Well, probably definitely graviton, right? I mean,
probably, right? Because otherwise there'd be no mechanism for inflation to actually expand the universe.
Yeah, but
so wait, like because if the gravitons didn't exist, there'd be no sort of communication between inflatons, or
I mean, I wouldn't say existent is a good word, because if you have a physical model that contains the inflaton and gravitational field, then de facto there will always be possibility of the corresponding particle that exists, right? Like the graviton will always be there, the inflaton will always be there. But whether or not we can actually grab one, hold it in our hands, and examine it, I mean, that's a different story. So from that regard, we'll probably never find an actual inflaton particle, because they have so much energy in them. We'll never have enough energy budget to make one, right? But as opposed to graviton, we actually have captured some in these gravitational merger events, which maybe we'll discuss them in a future episode. But probably like an actual inflaton, probably not, right? Like I don't think we'll see.
Oh, there's no way.
Yeah, there's no way. Like basically, yeah. So
it's archaeology.
And it's not just because it's like higher energy, but just is it the question of like answering what dark energy is, or is it actually creating the high energy conditions to produce an inflaton way back in the early universe?
I would say, well, what the particles we don't care so much about, right? Like the particles associated with those fields can have very different properties, right? Like the inflaton probably has huge mass.
I mean, it's like what we said about the ball rolling down the hill. Like once the ball rolled down to the bottom of the hill, the inflaton stopped being stable, and that's why it started producing all of this other material. In order to produce an inflaton, you would have to. You could do it by if you had a dial that could increase the density of dark energy, and you could turn it up to like 100,000 times higher than it is right now, then maybe you'd have a chance of creating the inflaton. But that's like so far beyond the realm of what anyone can conceive of doing.
Yeah. I guess last question, and then we can leave with some concluding remarks. Is just like what? Now I forgot the question. You know what? Let's just jump to concluding remarks. Yeah. So we're at time. What do you guys want to leave the audience with?
People call the Higgs boson the God particle. And if you're looking at like a very human-centric view of the universe, I think that's fair. Um, but if you're looking at like the story of creation, like what is the particle that is most closely associated with what we consider to be the creator of all things? That would have to either be the inflaton or the graviton, or some kind of interplay between those two things. Like the Higgs boson didn't even come into existence until way after the universe
Way after, yeah.
was born, right? So it's just kind of weird to call the Higgs boson the God particle, just because it didn't even exist at the beginning of the universe, and certainly God did, if there's a God. So,
Yeah,
we would like to be firm in our assertion that the Higgs boson is not the best candidate
yeah. Well,
for
I
a
mean,
particle to be called a God particle.
I want to clarify that we are in no way condoning the use of the word God particle.
I am.
You are, yeah. But okay, but at least not for me. I thoroughly do not like that framing, but that's fair. Okay, that's fair. Like obviously,
Would the creation particle feel better for you?
maybe
Because if you say the creation particle, like half of America is just gonna hear that and just think God.
Well, hear me out. Like I don't like that phrase, but if it gets people's attention to think about particle physics, I think it did a reasonable job. But in a sense, the Higgs really did not participate very much in the cosmology of our universe, and I would say that. Even though people are familiar with the God's particle, not a lot of people are familiar with the scientific physicist view of the story of creation. And I think, if we really go down this route, thinking about God's particle, the inflaton will really fill that role to when people study the inflaton, look at all the science behind it, they'll get themselves familiar on how physicists thinks about a scientific view of creation. And this is a very, sure, some of it is speculative, but it's the best we've got. And it's quite intricate and quite interesting and plausible as well.
It's not that speculative. There's so many disparate pieces of evidence all pointing at the same thing. And it's the only conceivable,
right. Well, it's the only reasonable thing, but of course,
up to our lack of creativity.
Yeah, probably. But I mean, at the end, it doesn't have full experimental evidence support yet. It probably has some indirect.
It never will.
It never will, right? But I think that's
probably. When you have one idea that solves 20 paradoxes,
it's probably
it's like statistically speaking, it's usually when you have that kind of a situation, it's turned out to be valid.
It's probably one of the best top 5 ideas, or maybe even top 3 in the recent decades.
It's really hard to dispute.
It's not easy. So
we didn't even get into all of the if you just assume the Big Bang without inflation, nothing makes sense about the very first few moments. There's just so many paradoxes, and you just have this one simple idea, and suddenly all of those paradoxes melt away.
So given all that, I think I'll happily worship Inflaton as the God's particle if we have to have one. So
yeah.
All right then. Well, on that note, I want to thank everybody for joining us. We'll see you all next.